Now we will talk about convex optimization. This is a bunch of inequality. So for different audience, so if you are domain expert, you better know everything in this slide and you know how to prove them. But if you are using it, then you just need to know the inequality and that's it. Don't worry by scale by this slide. You can go to this document. I have 100 pages on explaining everything. We are going to talk about the red thing. That is Jensen's inequality, subgradient inequality, strongly convexity, two definition, and the sweetness. If you are an outsider, you are just using it for your purpose. You just need to know how to use a formula. You don't care what does it mean. You don't care about how to prove it. Don't put too much burden on yourself. But if you are expert or if you are doing in this area that you will use this all the time, please do try to understand why the heck this is true. So that's what you need to do. Okay, always know up to this. That's the idea. Because math have infinite number of content, your life is less than infinite, you need to stop at some point. Okay. So now we are going to talk about convexity at intuition level. So basically it means what? Why the heck this is true? You just have a feeling. You don't need to prove it. That is, I can tell you there are 5 sentences, right? If you start from 1, you can prove 2. If you start from 2, you can prove 3. If you start from 3, you can prove 4. You can start from 4, you can prove 5. And if you start from 5, you can prove 1. Do you need to know all their proof? No. You just know they exist, know how to use them, and know their meaning. Then done. So what I'm going to do is talk about this at understanding level. You don't need to go too much about the math detail. It's a waste of your time unless you are doing a PhD in this area. Okay. So what the heck is convexity? A set S is convex if WV this is true. So what the heck? So I have a region S. I draw a shape. This is my S. So for any WV, so I have a W here and I have a V here. Okay. What the heck is this? So I have this thing, alpha 0 and 1. So what happens if alpha is 0? When alpha is 0, this is 0. This is 1 minus 0. So V, I have V. So when alpha is 0, I have V. This is alpha equals 0. What about if alpha is 1? Alpha is 1. This is gone. 1 minus 1, gone. But I have a W. So this is alpha equal 1. Okay, now what happens if alpha is half? Alpha half is half. So alpha half is what? I have half W plus half V, right? What does it mean? Half, right? So what about other value? So basically it's this line, right? So what does it mean? It means if I have 2 points, W and V, inside the set S, the line between them must be inside the set S. So that means what? That means I have a point here, I have a point here. Is this line inside the set? Yes. I have a point here, I have a point here. Is this line in the set? Yes. So for any 2 points, no matter how you draw, you always have a line conjoining them and it's inside this set. If this is true, then this set is a convex set. Then what is a non-convex set? Well, this sentence is false, right? So for example, what is a non-convex set? For example, this L shape is not convex. Why? Because if I have a point here and if I have a point here, this line I draw on them, this part is not inside the L shape. This is L, right? Because this means everything in W and V. Okay, this is my W and this is my V. Is it true? Yeah, this part is true. But is this implication true? No, because this part is not true. So therefore, this is false and this is not convex, right? Or is this shape convex? No, this shape is not convex because I have this. Okay, and there are some extreme case. For example, is a straight line convex? Yes, because inside a set, this is my straight line S. Where can you be for the W and V? Well, we can only be on the straight line, right? So you either have these 2 lines. Is this part inside the straight line? Yeah. And then let's say you have another 2 points is here and here, ending point. Is this line inside the straight line? Yeah. So straight line is also convex. And then similarly, is a triangle convex? Well, you have a triangle. So you have a point here and you have a point here. Is this line inside the triangle? Yes. So therefore, it's convex. So now, this is a set is convex. Now it is a function is convex or not. So you have this so-called Jensen's inequality. By the way, this is not J. This is not Jensen. This is Yang. Okay, pronounced as Y. So what the heck is there? So now you have a function. It is convex. How do you know it is convex? Draw this. Do not try to understand the expression. Sometimes expression is very hard to understand. So you draw a function. So I have a x. Okay. Now I have what? I have a function. Let's say I have a function like this. Okay. This is my f. Now again, look at what the heck is this? Yellow. Yellow. It's I just said, right? What's yellow? Yellow is exactly the line segment thing I talked about previously, right? So now what the heck is yellow? A line segment. So I have 2 points. Let's say this is my W and this is my V. Then what is yellow? This is yellow, right? Now, what the heck is this F of yellow thing? f of this yellow thing means I take all this part map to my f, right? So therefore, this whole thing, let me draw in green, thick green. This whole thing is after the f, right? So therefore, this thick curved part is this part, right? Now, this is done. What the heck is this part? Let's talk about it one by one. So I have my FW. So FW, this is my FW, right? This is FW. What the heck is FV? I have my V, go to here. This is my FV, right? Okay, this is my FV. What the heck is this whole thing? Looks like this, right? So actually, this whole thing, now I change color. FV in blue. This is my blue. This is my blue. So I have a blue thing, right? And technically speaking, it should be these 2 points. So I have this thing. So now I have a picture, that is, I have a green line, and then I have a green line under my blue chord. So what the heck is this? Basically, it means I have this, and then I have this. This U thing is this part. This line is this part. So it's saying if my f is convex, this line, a chord, must be always above my function. So it means chord above function graph. And this is true. This is a convex function. This should be easy to illustrate, because if my function looks like this, is this convex? No, because I can have a point here and I can have a point here. I have drawn a line. This part is not above my function. This is the same thing, right? If I have a line inside the whole set, this is a convex set. But if my shape is like this, this line, this part is not inside the set. So this is the same idea. You can think of this whole thing. If I fill in the ceiling, this is a set. Is this a convex shape? No, because this part is outside my set. So this is the definition of this Yang-Sen's inequality. So you should have a mental picture of all this thing one by one. What the heck does it mean? It means look at this part, the green, it means this green. Look at the yellow, this means the yellow. And part by part, if you understand the picture, you should understand the whole thing very well. Okay, go to the next one. So you can have the probabilistic version. What is the probabilistic version? The probabilistic version is the following. If I have a function h, what is h? H is a random input, real number output, because input is D, this is a random distribution. That means I have a random variable. And then E is what? Is the expected value of a random variable. If you remember what is expected value of random variable, expected random value of random variable is this. Okay? So on average, what's the behavior of this? And then if this average behavior, input inside H, is smaller than after you do the function and take the average, if this is true, then this is also convex. And why? Because this is these two are the same thing. You can think of this as half, 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 half. And suppose W and V are two random events, and you only have two events, then this half W, half V is exactly average of this random variable, right? And what about here? It's the half after the F. So it's the half. That means average. So that means these two are the same thing, in a sense. Okay? So that's how you understand convexity. You don't need to do the proof. You just need to understand concept. And what's the good thing about convexity? Is it about you have solution? No. It is possible. Be careful. Solution exists. Solution unique. Solution global are three different things. You have three things and you have 8 cases. That means you have a table and you have 8 cases. That is take, not take, and so on. So do not mix up these three things. Exist, unique, and global are not the same thing. Convexity give you the following. Convexity give you if f is convex, all minimizer must be global. That means what? There is no local. Convexity means no local, all global. So this function is convex function. This is the smallest value you can get. This is global. Nothing is below this. But this is also a convex function. And everything here are global minimizer. But how many of them? Infinitely many of them. And similarly, this is also a convex function. And everything here are global minimizer. And in the other sense, I can have a function that looks like this. Okay, this is not a convex function, but I do have 3 global minimizer. Do I have local minimizer here? I do not have local minimizer because all the functions at the minimizer are same value. But if I have a function that looks like this, then this is a global minimizer, this is a local minimizer. So now you see, this is not convex, but all local are global. This is all local are global, only one. All local are global, many. All local are global, many. Then they are all convex. This one is not convex. I have 3 solutions, but all local are global. This one, I only have 1, not convex, and only 1 global and 1 local. So global or not is because of convexity. Convexity only says no local minima. All local minima are global. It says nothing about how many of them, or do you have only 1, or does it have exist? By the way, there's function convex, but you don't have solution. For example, minimizing y equal x. Yes. Where is the minimizer? Negative infinity. So this function is a convex function, but the minimizer is at infinity, which we cannot get it. So therefore, no solution. So this is important. Convexity only tells global. It tells nothing about how many of them does it exist or not. This is important, okay? Now, after all this thing, we now go to another thing. This is called differentiability. So we just talked about the convexity, right? What's that? The chord about function graph. So this picture, okay? Now, here's another thing. This is called subgradient convexity. Because sometimes we will have function that we cannot take derivative, so we need some other way to describe it. So let me recall, if I have a function that's convex, I will have what? A chord like this, right? So you can imagine this is like I have a convex shape, and then I draw a line inside myself. And this line is inside myself. No matter how I draw the line, then this is convex. Then what the heck is this slide talking about? This line is like the opposite image. I have a function. Now I do not draw inside myself. I don't care about black anymore. I care about outside. I care about this. What the heck is this means? This is a slope, right? This is a slope at this function at this point. Here's the thing. If at a function point of view, I have this, my f, and I have a point here, and I can draw a slope, which is looks like this, then this particular slope is the slope at this point, right? Now, if I generalize this notion to any f, including this funny f, what is this funny f? This f is I change my behavior at this point, Then, first of all, is this function differentiable at this point? Classically, it's not differentiable. Why? Because let's go back to calculus. What is the differentiation here? It is the slope from here approaching to this x, which is the slope here, and the slope from here approaching to this value, which is the slope here. This slope, let's say the slope is 2. This slope, let's say the slope is 1. Is 2 equal 1? 2 is not equal 1. So this point do not have derivative. So therefore, you cannot have slope at this point. It's not differentiable. But now let's say I don't care about differentiation anymore. I said any red line that touch my point at this particular line is a slope. Then this is below my blue. So that's why there's a sub. And this is a slope, right? So it's a gradient. So what I'm saying is that if I have this red line, then this is below me a subgradient. The important part is I can have more than one subgradient. This is also a slope, right? And to be extreme, I follow this line completely and I pass through this point. It's also a slope, right? So the sense is at this particular point, I have infinitely many slopes, and all of them are slope at this point. And how do I describe it? So basically, it's this thing. This is my blue thing, my f. This is my f, okay? At any y, so this is any y. So suppose my y is here. This is my y. Then fy is, this is my fy, okay? This is my fy. Okay, what the heck is this thing? This thing is the red thing. I have an fx, and then I have this thing. So this is my x. Then, so suppose you have this part. What the heck is this part? This part is y minus x multiply the g. G is the slope. For one-dimensional function, g is slope. So it's like 3x, 4x. So 3x is like this, 4x is like steeper, right? So basically saying at this particular point, I can have a number g such that if this part, which is this line, is below my blue, then this is a slope. And notice that what happens if the x here is y. If this value is y, then y minus y gone, I don't care. And I have fy equal fy, which means I touch this point, right? So in other words, it means, what's subgradient? I have a tangent. This is a tangent that's below me. Tangent means I touch it. And now the tangent slope, that means this g is the slope of this point. And because I can have many tangents, so possibly more than one. And this slope is so interesting, so I give a special name called subgradient. And because it's more than one, so every subgradient correct together inside a set, I call it subdifferential. That means now I can differentiate something not differentiable. This is to be used for what? For this crazy function. Because I want to do gradient descent, I need to d something. But now I have this kind of on-off function that is not differentiable, so I need subgradient to d these people. So that's the purpose. So this is the first hard part, okay? You just need to get the idea. You don't need to get the math too much, okay? Now, another one. So this is what? This means I have a slope below me for not differentiable case. Here's another one. I have strong convexity. So go back to Yang-Sen's inequality. What's Yang-Sen? This thing, right? So Yang-Sen means I have a function that is convex. Then now suppose I have f and I subtract a quadratic function, and if this is still convex, that means what? That means after subtracting a quadratic, your f is still convex. So that means if you don't subtract it, this guy is at least as alpha-ly curved. So this is an example. Suppose I have the red thing. What is this red thing? This red thing is exactly this part. It's exactly this thing. So the strong convexity basically means I have a red thing. I add a new thing, which is the green thing. And what is the green thing? The green thing is the gap between me is a quadratic function. This two picture looks very similar, but the gap here is not a quadratic function. Because if you look at the gap here, this is a straight line getting smaller and smaller and smaller. Actually, the gap is a straight line, so it's a first order function. But here, the gap is getting bigger, and a quadratic goal. So in other words, if the gap is a quadratic function, that means you are at least as alpha-ly curved. Here it's not. So this is the two different things. Okay, so these two are the different convexity outside of this classical one. Okay, these are just basic math. Okay, you don't need to prove everything. You just need to know the idea for the application people. Okay, now we are now done with convex optimization.